Today's lecture pertains to cryptography based on the hardness of the discrete log problem. So before we dive in the subject, I will give a formal definition of the discrete logarithm problem. We've seen an example of that and it's coming in the next slide. It was the crypto system based, for the key exchange task based on the Diffie-Hellman protocol. Uses a discrete log problem. Today we're going to see that we can do a lot more, including encryption and digital signature. So we assume that we have a finite group, and for the purpose of this course, the finite group is always going to be the multiplicative group of elements that are invertible mod p. And we assume that we have some element in that group that we call G because it is the generator. And the discrete log problem is the problem of given the H that is in the group generated by G, find the power X such that H is G raised to the power X. So in our cases, of course, that has to be modded out by P. So in the following, we're presenting crypto systems that are secure if the discrete log problem is secure. In fact, this is a little more complicated than that, and it's something we've gone over in class. It's not completely equivalent, but at least these are crypto systems that rely on the idea that the discrete log problem is hard, and somebody who knows how to solve the discrete log problem would then be able to break the crypto system. Now, the discrete log problem is not always hard, depending on which group we're working in. But for a large enough p, the multiplicative group of integers mod p seems to be a very good candidate. Another one, of course, is a group of points of an elliptic curve over a finite field, but we're not seeing this in this lecture. And the idea is that Diffie-Hellman key exchange and, of course, the encryption and digital signature provide alternatives to RSA-based primitives. For a long time, people thought that it was a great idea to have, in the case of RSA not being secure enough, when we didn't have as much confidence as we have in RSA today, then we knew that a crypto system based on the DLP could be a good backup plan. So something we've already seen, it's actually the first instance of a public key crypto system, is the Diffie-Hellman key agreement protocol. So in this case, I'm just going to go over this really quickly. It's the same procedure as we've seen before. So Alice chooses an A and calculates G to the A mod P, where G and P are public parameters. And she sends that capital A to Bob, and Bob does the same thing. He calculates a B secret that he keeps for himself, and then calculates that capital B, which is G to the B mod P, and this is sent to Alice. And then both can calculate S, which is the shared secret, which is equal to B to the A mod P or A to the B mod P. But somebody who's tapping the communication channel will only be seeing capital A, capital B, and G, and P, of course. But that person, hopefully, is not going to be able to retrieve G to the AB. Okay. Now, somebody who can solve the discrete log problem will be able to do that, for example, by getting from A, getting small a, and then raising B to the power small a. But the problem of given A, capital B, G, and P, find G to the AB is the Diffie-Hellman problem. And in general, it's not known to be equivalent to the discrete log problem. So let's work on an example. So we have our parameters here. Now A, which is G to the A mod P, in this case equals 86. B, which is G to the B mod P, equals 89. And then if I raise A to the power B mod P, I get 8, and it just so happens to be b to the a mod p. Those two values are my shared secret that I can then use as a session key for example, establishing a secure communication with my favorite block cipher, AES, for example. Now let's see how we can produce an equivalent system as the RSA encryption scheme. So we call that the Gamal encryption scheme, and the public parameters are pretty much the same as for the Diffie-Hellman key agreement protocol. So it's a generator and a prime, or a generator and a group if you work in a more general setting, but in this lecture, again, the group is always Z mod P star. And then during key generation, Alice chooses a secret key, which is an integer between 0 and P, and she reveals the public key, which is G to the X mod P. Now let's see how to encrypt to send a message to Alice. So for the encryption, let M be a message, mod P. Bob chooses a random Y, still between 0 and P, and he computes G to the Y mod P. And then that G to the Y mod P is H to the Y times M is multiply together mod P, and that gives you C2. Now the encryption of the message is the pair C1, C2. Okay. Now let's see how to decrypt. Now Alice has the secret key X. So given C1, she can raise C1 to the power X to get H to the Y. Okay. So without necessarily knowing why, that's the important part. And she recovers M by simply inverting that element and multiplying it by C2 mod P. That gives her M. Let's see how that works on an example. So, for example, let's see, here we will have H. So X is going to be 43, and then H is going to be G to the X mod P, which is going to be 86. Okay, and so this is the public key, and the private key is X. Now we want to encrypt the message M equals 43. So what we do is we first calculate a random Y. So random Y, let's say 44. And then we calculate C1, which is G to the Y mod P, which equals 71. Then C2 is simply going to be M times H to the Y mod P, and that equals 70. Now, upon reception of this message, this ciphertext, which is C1 and C2, the entire pair is the message. Then we will look at, so we will raise first, we calculate S, which is C1 to the X mod P, and that is 58. And then we multiply C2 by the inverse of S mod P, and that gives me 43, which turns out to be my original message. So we showed how to use Gamal for encryption and decryption. Now let's see how we can, we have randomness here, which means every different encryption of M is different. So that seems like a necessary condition to achieve some form of security, but it is not enough in itself in the case of, for example, a CCA adaptive attack against Gamal. So we need like proper padding. Let's see briefly why this is the case. So remember the game between the adversary and the challenger. Let's say nothing happens during phase 1 and the adversary chooses 2 messages in the message space, sends them to the challenger, who encrypts one of these depending on which experiment we're in, and then sends the corresponding encryption to the adversary. Now the adversary is going to build a ciphertext from the ciphertext they received and request their decryption to the challenger. And what they do is they multiply the second coordinate of the ciphertext by the inverse of M0. So that creates a second ciphertext which is not equal to C. And for that, they're entitled to ask for the decryption of C. And the decryption of C is simply Mi times the inverse of M0. And then upon reception of that information, it's trivial for the adversary to decide which which Mi was encrypted in the original ciphertext C, because, well, if Mi times M0 to the inverse equals 1, then Mi is M0, otherwise it has to be M1. So it's actually pretty simple to challenge the security, the CCA2 security of Gamal if there's no form of padding that prevents the property of what we call so we were able to use this property that we can multiply by the ciphertext by message and get a new valid ciphertext. So we would need some form of proper padding to avoid this. Now, briefly, to finish, we'll look at the Gamal signature scheme, which is an equivalent scheme to the RSA scheme, the digital signature. And the way it works is the public parameters are the same. The key generation is the same as well, pretty much like RSA. And then the signature of a message works in the following way. First, Bob chooses a K between 0 and P that has to have GCD 1 with P minus 1. And then Bob computes R, which is G to the K, and sends the signature, which is a hash of the message minus XR times K inverse mod P minus 1. Think of this, of course, as mod P minus 1, and the random R. Then to verify, Alice verifies that G raised to the hash of M equals H to the R times R to the S mod P. And then indeed, we see that it is the case if the signature is valid, that H to the R times R to the S is simply G to the XR times G to the H of M minus XR. We see here that the K got killed by the power K, the K inverse mod P minus 1, and that gives you your verification. And only somebody with the private key would have been able to produce a valid signature. So that's it. Now, one last thing I want to say about Gamal signature and encryption is that in practice we're not really using it. We're using them because nobody found any kind of significant security flaw in RSA, which means that they're more theoretical alternatives to RSA that could be implemented if one day somebody found a serious security flaw in RSA.